Hi class, welcome to How To Video 6. In this video I'm going to show you how to calculate the mean difference between the pretest and the post-test. I'm going to show you how to use a dependent samples t-test to determine the statistical significance of that mean difference. I'm going to show you how to calculate the percent change of the mean difference between the pretest and the post-test. And I'm going to show you how to create a line graph to showcase the means and standard deviations of the pretest and the post-test. The data that we're going to be working with here today comes from a 6-minute walk test. The 6-minute walk test is a commonly performed test in the clinic and in the research laboratory. This test requires a large space. Typically it's done either in a hallway or in a gymnasium. And what you do if you're the tester is you get 2 cones and you set one cone at one end of the hallway and the other cone at the opposite end. And preferably you space them out about 30 meters apart if possible. And then with your subject, you tell that subject to walk as fast as possible, trying to cover as much distance as they can in 6 minutes. That's the objective of the test. Try to cover as much distance as you can in 6 minutes. And you have the subject walk in between the cones back and forth as many times as possible during the test. And then at the end of 6 minutes, you can determine how much distance they traveled in that time window. And the more distance traveled, okay, the further someone walks in 6 minutes, the better the performance. And it's believed, research suggests, that the 6-minute walk test is a good indicator of overall functional ability. And so, for example, someone who walks further during that 6-minute time period, it's believed that they have greater functional ability. Okay, that's an indication of greater functional capacity. And so again, the greater the distance, the better. The better the performance. Again, that's a good indication of good or great overall functional ability. Someone that can walk farther during the 6-minute walk test. Again, the 6-minute walk test is easy to perform. All it requires is a stopwatch to keep track of time, okay, and then some way to measure the distance that one travels. And then if you can do that, okay, you can use that 6-minute walk test. So again, it's very, very easy to use, and it's believed to be a good assessment of overall functional ability. Now, the population that we're going to be looking at today in this video is a disease population. They're patients with chronic obstructive pulmonary disease, or COPD. This COPD disease, it affects the lungs, and this 6-minute walk test is commonly performed in this patient population, in people with COPD. The data that you're going to be using for your assignment number 6 is also going to be 6-minute walk distance data. However, you're going to be looking at a different population. You're going to be looking at a population of patients with chronic heart failure. And again, very similar to COPD patients with chronic heart failure, this 6-minute walk test is commonly performed in this population. And so, yeah, so this is a very practical example that we're going to be looking at here today for our assignment 6, is 6-minute walk distance data in these populations. Again, this test is commonly performed in these types of patients with chronic heart failure, or in the video today we're going to be looking at patients with COPD. Again, similar to previous videos, because I'm looking at different patients than your assignment 6, my data is going to be different. And because my data is different, my answers may also be different than yours as well. So again, just keep that in mind. I'm going to, in this video, work the same problems, the identical problems that you have for your assignment 6. And so after watching this video, you should have a good knowledge, a good understanding of how to work those problems in your assignment 6 Word document. Again, your data is going to be different, so your answers may be different than mine. However, the process that I show today in today's video is going to be the same process that you'll use to answer your questions for your assignment 6. Okay, let's go ahead and take a look. Here's our assignment 6 Word document to the right, and then I've got a blank Excel spreadsheet to the left. And I've got these put up one next to the other, that way we can look at them simultaneously, just like we've done in previous how-to videos. I'm going to make these a little bit larger on the screen, that way it's a little bit easier there for you to see. Okay, before we start our assignment 6, make sure, first thing, type in your name at the top left corner of the page. Don't forget that. Okay, let's look at this scenario. It says, suppose a physical therapist wants to examine the effectiveness of an exercise program on 6-minute walk distance in patients with chronic obstructive pulmonary disease. The therapist measures the 6-minute walk distance of each patient before and after the exercise program. Below are the results. Copy and paste these data into an Excel spreadsheet. Use these data to answer the following questions. Okay, so this scenario right here, it kind of paints the picture. It gives our objective. The objective of assignment 6 is we're trying to determine if this exercise program is effective or not at improving 6-minute walk distance in these patients. To determine the effectiveness of the exercise program, we're going to perform a dependent samples t-test. That's the only way in order to determine if the mean difference between the pretest and the post-test is real. Is it statistically significant? We've got to use a dependent samples t-test in order to determine that. So that's the objective here today, is we're trying to see if this training program, this exercise program, is it effective at improving 6-minute walk distance in these patients with COPD. Again, remember, with your assignment 6, your population is going to be a little bit different. You're going to be looking at 6-minute walk distance data in patients with chronic heart failure. But still, it's the same concept. You're trying to determine, is this exercise program, is it effective at improving 6-minute walk distance in patients with chronic heart failure? Okay, it says up here what we need to do first is we copy and paste these data from the Word document into our Excel spreadsheet. So let's go ahead and do that. So let's copy and then paste. And we can expand the size of the columns. That way we see the labels and the values in their entirety. Okay, now that we've copied and pasted the data into the Excel spreadsheet, we're ready to go. Let's go to question 1. Question 1 says, what are the 6-minute walk distance means and standard deviations for the pre-test and the post-test? Report them as mean plus or minus standard deviation. Okay, so to do this, we're going to come back over to our Excel spreadsheet. I'm going to add those statistics here to the spreadsheet. I'm going to put them over to the right of the data. I'm going to type in the mean and then standard deviation, or SD for short. And then also too, I'm going to bold these statistics just to make sure they're a little bit easier to see, those labels. I'm also going to put labels for the pre-test and the post-test. I'm going to put these above here. These are going to be my labels for the columns. Now I'm going to use Excel to calculate the mean and standard deviation for the pre-test and the post-test. I'm going to put the mean and standard deviation for the pre-test here in this column, and I'm going to put the mean and standard deviation for the post-test in this column. Let's start with the pre-test first. I'm going to click on this empty cell next to the mean label I just created. To calculate the mean using Excel, I'm going to go to the function. I'm going to go to average. Remember, the mean is the average of the data. I'm going to click OK. And then I'm going to go over and I'm going to click and hold and drag to where I've highlighted all of the scores for the pretest. Each subject has a pretest score. I'm going to highlight all of those scores. Now that I've highlighted all those scores, I'm going to click OK, and that should calculate my mean for the pretest. If you take a look at question 1, it says we need to round the means and standard deviations to the second decimal place. If you look here, obviously it's not at the second decimal place. We need to adjust this. To adjust the number of decimal places, you can go up to Home, and then you can go up to this function here, Decrease Decimal. Click on it, and that decreases the number of decimal places to where we have 2. And remember, 2 decimal places, what does that mean? That's just 2 decimal places to the right, 2 numbers to the right of the decimal. And that's what we have. We have 7.3 to the right of the decimal, 2 decimal spots. Okay, very good. Let's go ahead and calculate the standard deviation for the pretest. To do that, click on my empty cell next to SD standard deviation. Go to the function key. Go to STDEV. Remember, that's the function we're going to use to calculate the standard deviation. Click OK. Same thing, we're going to click, hold, and drag, and we're going to highlight all the scores for the pretest. Once we've done that, click OK, and that should calculate our standard deviation for the pretest. Again, similar to the mean, we need to make this 2 decimal spots, round it to the first 2 decimal places. To do so, decrease the decimal to 2. Okay, again, 2 spots to the right of the decimal. Very good. Let's move on to the post-test. Same thing. Let's calculate the mean first. To calculate the mean of the post-test, highlight the empty cell, go to the function key, go to average, click OK. Now we're going to click and highlight all of the post-test scores. Once we've done that, click OK, and that should calculate the mean for the post-test. Let's adjust the number of decimal spots by decreasing the decimal to 2, and that should be our mean rounded to the first 2 decimal places, which is what we want. Let's do the standard deviation for the post-test next. Click on the empty cell, go to function, go to STDEV, the standard deviation, click OK. Click and highlight all of the scores for the post-test, and then click OK. Again, we need to adjust the decimal to where we have 2 decimal spots to the right. Now we have our standard deviation rounded to the first 2 decimal places. Okay, that looks great. Now we can input those means and standard deviations into our assignment 6 Word document for question 1. For the pretest, let's do that first. It says we need to report these values as mean plus or minus standard deviation. So let's report the mean here first. Pretest, mean is 295.73. We can copy and paste this plus or minus sign and then put it here in our answer. Again, it says for us to do it this way, report it as the mean plus or minus standard deviation. So here's our mean plus or minus. The standard deviation, if you look over at the Excel sheet, is 42.04 for the pretest. Let's bold this. And then just like with previous assignments, it's always good to include the units. Let's do the same thing. Let's include the units here for the pretest and the post-test. If you look back here at the top at the table, it includes the units here in parentheses. Remember, we're measuring 6-minute walk distance. 6-minute walk distance is typically measured in meters, and that's how it is in our assignment. Notice that we have in parentheses M, which stands for meters. Okay, again, that indicates to us that the distance is measured in meters. So let's include that here, the units, and again, we can just abbreviate meters with the lowercase m. Let's insert the post-test mean plus or minus standard deviation. The post-test mean, if you look over at the Excel sheet, was 325.47. Again, I'm going to copy and paste this plus or minus sign, and then I'm going to add my standard deviation for the post-test, which was 42.69. Again, the post-test was also distance, which was measured in meters. Okay, now we have our pretest and post-test means plus or minus standard deviations. Let's move on to question number 2. Question 2 says calculate the mean difference in 6-minute walk distance between the pretest and the post-test. In parentheses, it actually tells us how we're supposed to calculate the mean difference when we compare these two, the pre and the post-test. When we calculate the mean difference, comparing a pretest versus post-test, we take the post-test first and we minus the pretest. That's how we should do it when we're calculating the mean difference in this scenario. So let's do that here. Let's go first to our Excel sheet and calculate the mean difference over here. I'm going to type in my label for mean difference, and I'm going to bold it. And then I will put in my calculation for mean difference here in this cell. To calculate the mean difference, again, it's going to be post-test minus pre-test. So what we can do once we have this empty cell highlighted next to our mean difference label, click on the equal sign on your keyboard, then go to the post-test mean, click on the cell with the post-test mean, then hit the minus sign on your keyboard or the dash line, then click on the cell with the mean pretest value, which is this one here. Now that we have our formula in place, basically what we've done is the same equation over here in our Word document. It's the post-test minus the pretest. Look, it's the G3 cell, okay, which just so happens to be my mean for the post-test minus my F3 cell, which just so happens to be my mean for the pretest. Again, you can do the same thing for your assignment. Post-test minus pretest. Once we have that, click enter, and that should calculate our mean difference. If we need to, we can adjust our mean difference. Yeah, it's good to have it rounded to the first two decimal places, just like we had for our means up above and standard deviations. Let's report this mean difference now down here in our assignment for question number 2, 29.73. And again, let's include our units, which is meters. Now, what does this mean? We just calculated a mean difference of 29.73 meters. It's a positive 29.73 meters. So what does that mean? That just means that the post-test is larger than the pre-test. The post-test 6-minute walk distance was larger than the pre-test 6-minute walk distance. Therefore, we got a positive mean difference value of 29.73 meters. What does that mean in the grand scheme of things? Well, that means that the exercise program that we're testing to see if it's effective or not, this exercise program did elicit an increase in 6-minute walk distance. It did. It listed a positive increase. Because this value is positive, we know it's an increase of 29.73 meters from the pre-test to the post-test. Now, what we're trying to solve, remember, for assignment 6 is we're trying to determine, is this mean difference statistically significant? And that's why we have to use a dependent samples t-test. That's the only way to determine if this difference here that we just calculated, is it statistically significant or not? Is it real? Is it reliably different than 0? Again, the only way to answer those questions is to perform a dependent samples t-test, which we will in just a minute. Okay, let's go ahead and move on to question 3. Question 3 says, what would the null hypothesis be for the mean difference in 6-minute walk distance between the pre-test and the post-test? It talks about this in the PowerPoint, so please refer to the PowerPoint for more information on the null hypothesis when we're comparing the pre-test versus the post-test. But we can include something here for our assignment 6 like this. We could say that the null hypothesis is the mean difference, and let's be specific here for our assignment. Remember, we're looking at the mean difference of what? We're looking at the mean difference in 6-minute walk distance. So let's include that in our answer. Let's be specific to what we're actually looking at in this assignment. So let's say the mean difference in 6-minute walk distance between the pre-test and the post-test is not statistically significant. So yeah, that's the null hypothesis. When we're comparing the pre-test versus the post-test, we could say something like this. And you could say something exactly like this, okay, for your assignment 6. That the mean difference in 6-minute walk distance between the pre-test and the post-test is not statistically significant. Now, if you refer to the PowerPoint, there are alternative ways to state the null hypothesis. And one of the alternative ways is talked about in the PowerPoint, and I'm going to include it here in parentheses in my answer. and you can do the same thing on your assignment 6 as well. You could say that the difference between the pretest and post-test means is 0. So yeah, it talks a little bit about this in the PowerPoint, but this is an alternative way to state the null hypothesis, that the difference between the pretest and post-test means is 0. And so again, that's what we're testing. When we use a dependent samples t-test, which we will, okay, and we'll perform that for question 4 down below. When we perform that dependent samples t-test, we are testing the null hypothesis. We're testing what we just got through stating here in question 3. We're testing to see if that mean difference is statistically significant or not. Remember, the null hypothesis states that the mean difference between the pretest and post-test is not statistically significant. Again, another way to say that, I included in parentheses, is the difference between the pretest and post-test means is 0. And so again, remember, what does that mean? That just means if we look back here at the mean difference we calculated earlier, we're trying to determine, is this mean difference, is it reliably different than 0? Is it statistically significant? Is it real? And again, the only way to determine that is to perform a dependent samples t-test. And so again, when we perform that dependent samples t-test, we are testing this null hypothesis here. Okay, let's move on to question number 4. 4 says, suppose the physical therapist sets their alpha level at 0.05. Perform the appropriate t-test in Excel to determine if the mean difference between the pretest and the post-test is statistically significant. Copy and paste the final output for your t-test as a picture in the space below. Make sure it is large enough for me to see. Okay, so if we go back up here, it says perform the appropriate t-test. If you look at the PowerPoint, it talks about there's 3 different t-tests in Excel. Now, there's only one dependent samples t-test. The other 2 t-tests are independent samples t-test. Again, that's what we did in the previous assignment. This assignment, we're going to use a dependent samples t-test like I said earlier. Why are we going to use a dependent samples t-test? Well, it talks about this in the PowerPoint, but if you take a look back at our Excel sheet at our data, take a look at the subjects. We have 15 subjects in this data set. Each subject has a pretest score and a post-test score. Because we're testing the same subjects twice, we tested them at the pretest and we tested them at the post-test. When we do this, when we test the same subjects twice, we know for a fact that we're going to use a dependent samples t-test to analyze those data. We're not going to do an independent samples t-test. An independent samples t-test is when we compare 2 different independent samples or 2 different independent groups. When we test the same group of subjects and we test them twice, that's when we perform a dependent samples t-test, or also called a paired t-test. And if you look in Excel, that's actually the first t-test that's listed. It's the t-test paired 2 sample for means. That's the t-test in Excel that's equivalent to a dependent samples t-test. It's the same thing. So in Excel, to run a dependent samples t-test, that's the one that we're going to perform. It's the t-test paired 2 sample for means. The other 2 tests, like I said earlier, those are independent samples t-test. That 2 sample assuming equal variances and the 2 sample assuming unequal variances, those independent samples t-tests that we talked about in the last assignment, again, those are not dependent samples t-tests. Those are independent samples t-tests. For this particular assignment here, again, because we're testing the same subjects twice, we're going to use a dependent samples t-test, and in Excel, it's called a t-test paired 2 sample for means. Now that we know what t-test to run, which one to perform, which is appropriate, let's go ahead and do it. Let's go over to our Excel sheet and perform that t-test. To perform the t-test in Excel, go to Data, go to Data Analysis, scroll down to the bottom and you see those 3 t-tests I was talking about. Remember, these 2 right here, that's what we looked at the previous assignment. Okay, these are two examples of independent samples t-test. Okay, these 2 t-tests are independent samples t-test. This test here, that's the dependent samples t-test. And so again, because we're testing the same subjects twice, this is the one we're going to use. This is the dependent samples t-test, also called a paired t-test, so it makes sense that this is the one that we're going to choose, this paired 2 sample for means. Once we have it highlighted, click OK. Next, we have this screen. And this screen here, we're going to select and insert the appropriate data and the appropriate values. Let's start with variable 1 range. If you click inside the box here like I have to where my mouse or my clicker is blinking, for variable 1 range, we're going to include all of the scores for the pretest. So I'm going to now click and hold and highlight all the scores in the pretest. Once I've done that, then I'm going to go to variable 2 range. I'm going to click inside that box to where my clicker is blinking. For variable 2 range, I'm going to include all of the scores for the post-test. To do this, with my clicker blinking in the box, I'm going to go over here. Starting at the top, I'm going to click and hold and drag to where I have all of my scores highlighted for my post-test. Now that I have the data selected for the pretest and the post-test, let's move on to the next one, hypothesize mean difference. Remember, when we're testing the dependent samples t-test, we're essentially testing that null hypothesis that we wrote up here in question number 3. Remember, one way to word the null hypothesis is what I have in parentheses. The difference between the pretest and post-test means is 0. So what are we going to put here for the hypothesized mean difference? Yeah, we're going to put 0 here. Okay, because again, we're testing the null hypothesis, and that's what the null hypothesis says. It says that the difference between the pretest and post-test means is 0, so that's what we're going to put here for our hypothesized mean difference. For labels, we don't need to select labels, okay, so you can leave that blank. For alpha level, remember if you look at question 4, it says the physical therapist sets their alpha level at 0.05. Notice that the alpha level, the default, or at least the default here for me, is already set at 0.05. If it's not for you, make sure and set it at that value. Your alpha level needs to match up with what it states here in the question. The physiotherapist sets the alpha level at 0.05, so we need to set the alpha level at that value. So make sure the alpha level is set at 0.05, okay, like it is here. For the output range, click on output range to where it's selected, and then click in the box next to it. What we're doing here under this output options and for output range is we're going to select the area where our final output for our dependent samples t-test is going to go. Now we can click on any cell, we can put that final output anywhere we want, but typically it's best if we include it far enough away from our data to where it doesn't interfere with the statistics that we've already included or our individual data points here. So I'm going to click on, let's click on this cell here. Okay, again, it can be on any cell. Okay, but yeah, just make sure it's far away from your data. That way it doesn't interfere with anything. I'm going to click on this cell here. It highlights that cell. That's where we're going to put the final output. Now that we've included all of our values, okay, we've selected our data, inserted the appropriate values in the correct spots. Now we're ready to go. Let's perform our dependent samples t-test. We can perform it by now clicking OK. Okay, now we've performed our dependent samples t-test, and this is our final output for that test. Let's increase the column size a little bit. That way we can see everything. And you can do the same thing when you get your final output for your t-test. Okay, that looks good. It says here for question 4, once we have our final output, we need to copy and paste it into the space below. So let's go ahead and do that. Let's copy this, right click, copy, and then come back over to our assignment 6 Word document and paste it right underneath question 4 as a picture. Okay, there's that paste picture option there. Make sure it's large enough for me to see. To adjust the size of this, again, you can highlight it, go to picture format, and you can adjust the size up here. Okay, that looks pretty good right there. Okay, I'm going to delete some of the empty spaces here and bring up some of the questions down below so we can see them. All right, let's move on to question 5. Question 5 says report the appropriate p-value. Round it to the first 3 decimal places. So the p-value, where are we going to get that from? We're going to get that from the final output, which we just pasted for question number 4 here. Similar to the previous assignment, this final output looks very, very similar. We have the means here at the top. These are the means for the pretest and the post-test. And again, they should match up with our means that we calculated earlier in our Excel sheet. And it looks like they do. 295.73 for the pretest, 325.47 when you round it the first 2 decimal places for the post-test. That looks good. The variance right here, remember the variance from the last assignment? That was a very, very important statistic. Remember, that dictated what type of independent samples t-test we performed. If the variance was unequal, then we would perform a t-test assuming unequal variance. If our variance was equal, then we would perform a t-test assuming equal variances. And so variance was very, very important for our last assignment when performing an independent samples t-test. It dictated what independent samples t-test we were going to perform. And remember, with variance, in order to determine if the variance was equal or unequal, we looked at and we compared the standard deviations. Remember, the standard deviation is a measure of variability. For the dependent samples t-test, which is what we performed, or we just performed for question number 4, for a dependent samples t-test, the variance isn't as important. It's important. It's an important statistic for sure, okay, as well as the standard deviation. It's an important measure of variability. However, it doesn't dictate what test or what t-test we're going to do, not like last assignment. For this assignment, and if you remember, there's only 3 t-tests in Excel. And that first one, which is the one we just did, that t-test paired 2 sample for means, that's the only dependent samples t-test in Excel. So unlike independent samples t-test where we had to choose, we had to make a decision on which one we were going to do, for this, for dependent samples t-test, it's fairly easy. There's only one dependent samples t-test. It's this one. Okay, so it makes our decision process very, very simple. We know when we want to do a dependent samples t-test that this is the one that we want to perform when using Excel. And so again, variance, right? It was very, very important in dictating the type of independent samples t-test that we did for last assignment, for assignment 5. However, for this assignment, assignment 6, for dependent samples t-test, it's not as important. Okay, but again, it's still important to report measures of variability like standard deviation with our means, and that's what we did for question number 1. Observations, you'll notice we have 15 for the pretest. We also have 15 for the post-test. What does that mean? That just means the sample size. And so, yeah, again, if you look back over our Excel worksheet, we had subjects, we had 15 subjects in this data set. Each subject performed a pretest, each subject performed a post-test. So we have 15 pretest scores, we have 15 post-test scores. And so, yeah, it makes sense that, yeah, 15 and 15, okay, that's the sample size. That's the sample size for the pretest and the post-test. And again, the sample size typically is the same. When you run a dependent samples t-test, okay, the subjects you test, the number of subjects you test in the pretest is the same number of subjects you test in the post-test. And in this case, it was 15. The Pearson correlation, that's the next statistic here in our final output. If you take a look at the PowerPoint, it talks about this. When we conduct a dependent samples t-test, there is a correlation between the pretest and the post-test scores. And that should make sense. And again, it talks more about this in the PowerPoint, so please refer to the PowerPoint for more details on this concept. But that should make sense. The same subjects that perform the pretest are also performing the post-test. And so their pretest score is going to be related. It's going to be correlated with their post-test score. So it makes sense that we would have a correlation between those two, between the pretest and the post-test. And so when we compare subject scores, when we test the same subjects twice, yeah, we should expect a correlation between those two. And we see, and if you remember back from a couple assignments ago, we looked at correlations, and specifically we looked at that Pearson correlation coefficient, that R value. Remember, that was the statistic that we used to examine the correlation, to examine the relationship between two variables. And so again, we can calculate a Pearson correlation coefficient between the two scores, between the pretest and the post-test in this example. Now, if you remember from correlations, when we talked about those, you'll remember that the magnitude of the correlation coefficient, the magnitude of the R value, that dictates the size of the relationship, the size of the correlation. And we talked about that a correlation coefficient or an R value of 0.4 or higher is indicative of a moderate to strong relationship. A moderate relationship was a Pearson correlation coefficient or an R value of 0.4 to, I believe, 0.69. And then a Pearson correlation coefficient of 0.7 and above was indicative of a strong correlation or a strong relationship. And we should expect that. We should expect when we do a dependent samples t-test like we just did, where we're comparing pretest versus post-test scores, we should expect at least a moderate to strong correlation coefficient between those two scores. And sure enough, if you take a look at our value here in the final output, we observed a fairly strong correlation, a correlation coefficient of 0.78. That's indicative of a strong relationship. And so yeah, so you should see that for the most part. When you do these dependent samples t-tests, you should see at least a moderate correlation, at least a correlation coefficient of 0.4 or higher when you do these dependent samples t-tests and look at the relationship between the pretest and the post-test. The hypothesized mean difference, remember, is 0. Remember, when we do this dependent samples t-test, we are testing the null hypothesis. The null hypothesis states that the difference between the pretest and post-test means is 0. So yeah, that's the hypothesized mean difference, 0. The DF represents the degrees of freedom. Remember, we talked about this before. Degrees of freedom is influenced by sample size. The larger the sample size, the greater the degrees of freedom. And the greater the degrees of freedom, the more statistical power you have. And remember, statistical power, that's a good thing. If you have more statistical power, you have a greater chance of seeing a statistically significant mean difference. And so yeah, the greater the degrees of freedom, the more statistical power, the greater chance you have of seeing a significant mean difference between, like in our example here, between the pretest and the post-test. The t-stat, or the t-statistic, this next one here, again, you don't need to be too concerned with this one. In addition to testing the mean difference, when we perform this dependent samples t-test, right, we're trying to determine if that mean difference is statistically significant. When we do this dependent samples t-test, in addition to the mean difference, we're also assessing this t-statistic. And just know that the higher the t-statistic is, the greater the chance we have of finding a statistically significant mean difference. That's all you need to know. And don't worry too much about the sign in front of it. Okay, so if it's a negative or a positive, don't worry too much. Really just focus on the magnitude, okay, or the absolute value of this. If we were to make this positive, what would this value be? It would be 4.1. Okay, a t-statistic of 4.1 in this example. And so yeah, so just look strictly at the magnitude, the absolute value of that t-statistic. The higher that t-statistic is, again, like I said, the greater the chance of us finding a statistically significant mean difference between the pretest and post-test scores. Now, the next set of statistics here are very, very important. Here we see P1-tel, and then down below we see P2-tel. If you look at question 5, remember that's what it asks us to do. It asks us to report the appropriate p-value. So we know from our final output, okay, it's going to be in between this one and this one. Which p-value are we going to report? Are we going to report this P1-tel or this P2-tel value? Which one is the appropriate p-value? Again, it talks about this in the PowerPoint, but we're going to report the P2-tel test. This P2-tel value, that's the appropriate value that we need to report, the appropriate p-value. It talks about this in the PowerPoint. We also talked about this for the last assignment as well when we did independent samples t-test. Again, for independent samples t-test, we also use a P2-tel value. Okay, so same thing, just like the independent samples t-test last assignment, this dependent samples t-test, this is also the p-value that we're going to report, this P2-tel value. Remember that researchers generally frown upon the 1-tel p-value, and most researchers use the P2-tel. So because most research uses this P2-tel value, we as a class are also going to report and use this P2-tel value as well. We're not going to report the P1-tel, we're going to report the P2-tel value. This is the appropriate p-value here that we're going to report. And that's the same p-value that you're going to report for your assignment number 6. So for my P2-tel, which value am I going to report here for question 5? I'm going to report that p-value that's in the final output there. And if you take a look at the P2-tel, it's 0.001. And then if you take a look at the fourth number, okay, to the right of the third, and again, remember, it says round to the first 3 decimal places. So we have 3 decimal spots, right? 1, 2, 3. If we take a look at the fourth value to the right of the third, okay, and so if I take a look to the right of this 1, it's 0. What does that mean for this 1? Am I going to round up or am I going to keep it the same? Because it's less than 5, okay, this 0 is less than 5, I'm going to keep it the same. I'm going to keep it at 0.001. I'm not going to round it up. Now, if this number right here to the right of the third number, to the third decimal spot, if it's greater than 5, then yeah, you're going to round it up. But because in my example here, it's a 0, which is less than 5, I'm going to keep it the way it is. Okay, so yeah, so rounded to the first 2 decimal places, what's my answer? Again, I'm going to read this P2-tel. That's the p-value I'm going to report. It's 0.001. So that's going to be my answer here for question 5 for the appropriate p-value. Now, before we go on, I talked a little bit about this in the last assignment, these t-critical values for the 1-tel and 2-tel. Basically, what these are is the t-tels that are the t-statistics that are required in order to observe a statistically significant mean difference. And again, that's all you need to know. That's all you need to know is that these are the critical t-values that are required to observe a statistically significant mean difference. Okay, and so again, without going too much in detail, you can actually compare. For example, you can actually look at this calculated t-statistic that I was talking about earlier, and you can compare this value with the critical t-statistic, which is down here. And so these t-critical values, that's what you can do with them. You can compare their values with the calculated t-statistic, and if this t-statistic, like in this example here, like I said, again, if we just look at the absolute value, so in this case 4.1, because this value 4.1 is greater than the critical t-value for a 2-tel test, which is 2.1, because this value here is greater than this value, that's another way in order to determine if the mean difference is statistically significant. And so because this t-statistic that we calculated up here in our final output is greater than this critical t-value, then yes, okay, the mean difference is statistically significant. And that agrees with our p-value, right? Okay, again, that's for question number 6. But yeah, a p-value less than or alpha level 0.05 indicates statistical significance. And so yeah, so that does agree with our p-value, okay, that this t-statistic is larger than the critical t-value. Therefore, we have a statistically significant mean difference. If the t-statistic was less than this critical two-tailed value, then we would not have a statistically significant mean difference. Okay, so if the t-statistic, again, just looking at the absolute value, if it's less than this t-critical value, okay, then it would be no statistically significant mean difference. And so yeah, so again, just FYI, just a little bit of extra information there, how we can use this t-statistic and this critical t-value. And remember, for the critical t-value, just like with the p-value, we want to use the two-tail. Okay, we don't want to use the one-tail. Okay, we don't want to use the one-tail for the p or the t. We would use the t-critical two-tail. Okay, and then we can compare our t-statistic to that critical t-value to determine if our mean difference was statistically significant or not. So again, just a little bit of extra information, just FYI, okay, what those statistics are and how we can use them to determine statistical significance. Again, just an alternative way to use it and to determine significance. Okay, it says in question 5, based on this p-value, should the null hypothesis be accepted or rejected? Well, I kind of said it already, but yeah, this p-value here, 0.001, that we got from our final output for the p-two-tailed test, this value is less than our alpha level set at 0.05. So because the p-value is less than the alpha level, what are we going to do to the null hypothesis? The null hypothesis should be rejected. And so yeah, so anytime you have a p-value that's less than your alpha level, and in this case our alpha level was set at 0.05, if your p-value is less than the alpha level, then yeah, the null hypothesis should be rejected. Now, if the p-value is greater than the alpha level, then the null hypothesis should be accepted. And so again, your data, remember, is different than mine, and so you may have different answers than me. You could have the same answers. Okay, you could have a p-value like I did, where it's less than 0.05, and therefore you're going to reject the null hypothesis. Okay, or you could have a p-value that's greater than 0.05. And again, if it's greater than 0.05, then you're going to accept the null hypothesis. So again, to answer this question here, that's dictated by your p-value. Whatever your p-value is in relation to your alpha level, that's going to dictate what you're going to do with this null hypothesis. Should it be accepted? Should it be rejected? And in this example here, in this video, because my p-value is less than my alpha level, I'm going to reject the null hypothesis. Okay, moving on to question 6. Is the mean difference between the pretest and the post-test statistically significant? To answer this question, all we have to do is look at our answers back up here at question 5. Because we decided to reject the null hypothesis, and remember we rejected the null hypothesis because this p-value, 0.001, was less than our alpha level, 0.05. Therefore, we rejected the null hypothesis. By rejecting the null hypothesis, what are we actually doing? What are we stating? What are we concluding? We're concluding that the mean difference between the pretest and post-test in this example is statistically significant. So my answer here would be yes. Yes, the mean difference between the pretest and post-test is statistically significant. Why? Because we rejected the null hypothesis. By rejecting the null, that's what we conclude. We conclude that the mean difference between these time points here, the pretest and post-test, are statistically significant. So yes. Obviously, if you accept the null hypothesis, right, then what would be your answer? It would be no, right? If you accept the null hypothesis, then you would say that the mean difference between the pretest and post-test is not statistically significant. Okay, your answer would be no. So again, your data is different than mine. It could be the same. It could be different. Your answers could be the same. They could be different. And so, again, based upon your answers up here in question 5, that's going to dictate your answer here in question 6. By rejecting the null hypothesis in this example, we are stating that the mean difference between the pretest and post-test is in fact statistically significant. Okay, let's move on to question 7. 7 says calculate the percent change of the mean difference between the pretest and the post-test. To calculate the percent change, there's an equation in your PowerPoint, and it goes into detail on the percent change and what is it. But let's see if I can pull that over here to our screen and you can see. Yeah, here it is. This slide right here contains the equation to calculate percent change. We're obviously, for that question, going to use this formula to calculate the percent change in our assignment. And so, to calculate the percent change, this is the equation. It's a fairly simple equation. In parentheses, it's in the numerator, it's the x2 with the hyphen above it. What does that mean? That's the sample mean for the post-test, minus the x1 with the hyphen above it. That represents the sample mean for the pre-test. So basically, it's the post-test mean minus the pre-test mean divided by the pre-test mean again, and then multiply by 100 to get it into a percentage. When we calculate a percentage, yeah, we need to multiply it by 100 to get it into the correct units, to get it into a percentage. So this is the equation that we're going to use to calculate percent change for our assignment. To calculate percent change, I'm going to do that over here in Excel. I'm going to include that statistic over here, percent change. Okay, I'm going to bold it, and then I'm going to put my answer here, my percent change value, in this cell. To input the equation into Excel, I'm going to highlight this empty cell like I've done here, and then I'm going to click the equal sign on my keyboard, and then I'm going to proceed to type in the equation, this same equation, okay, that's over here in the PowerPoint. Again, I'm going to use this equation to calculate the percent change. Now, what I'm going to do here is I'm actually going to start off, you'll notice here in the equation I have a parentheses here. I'm going to actually include 2 parentheses. Okay, and I'm going to explain in just a little bit why I do that. But yeah, I'm going to start out with, and you can do the same thing in your assignment when you're calculating your percent change, put 2 open parentheses like I've done. Now we can proceed, okay, to put in the correct values. So remember, this x2 here is the sample mean for the post-test. And so the post-test mean we can take from here in our Excel sheet. Here's the cell with the post-test mean. I'm going to click on it, and then there we go. We put it in our equation, the post-test mean. Minus, if we put minus, okay, minus here, minus on our keyboard, minus the pre-test mean. Okay, this x1, remember, is the pre-test mean, minus the pre-test mean, so I'm going to select the cell with the pre-test mean. Okay, there we go. Now I'm going to close parentheses, okay, for 1. All right, I'm going to do a close parentheses 1 there, just for 1 close parentheses. And then next, remember this right here, expressed as a fraction, just means divided by. And so I'm going to, on my keyboard, I'm going to hit that slash button here, which represents divided by. And so divided by, and again, we're dividing by the pretest mean again. So divided by the pretest mean. So again, I'm going to select that cell with the pretest mean. Then I'm going to hit shift, and I'm going to do another close parentheses. And to do those parentheses, again, it's just shift, and to do an open parentheses like this one, okay, it's like shift, and then if you hit 9 on your keyboard, shift and hold, and then hold shift and then click 9, that's an open parentheses. To do a close parentheses, if you hit shift and hold and then hit a 0, that's close parentheses. That's how you create those parentheses using your keyboard. Again, remember I included 2 parentheses at the very beginning. The reason I did that is because I want to make sure that Excel performs the equation the way that I want it to. And so to help ensure that, that's why I put 2 open parentheses signs here. Basically what this has done is this has forced or it makes Excel do this part first. Okay, so by putting 2 parentheses, now what I've told Excel to do is I've told the program to do this first. So basically, if we look back over our PowerPoint, we're subtracting the means between the post-test and the pre-test. So post-test minus pre-test, I want it to do that first. And then divided by, what I want it to do second is I want it to divide it by the pre-test again. And so that's why I've included 2 sets of parentheses, because I want Excel to do this first and then followed by this afterwards. And so do you see how there's two steps here? This one's the first step, and then divided by, this is the second step here. To do those steps and to do them in that order, that's why I included those parentheses the way I did. And again, you can do it the same way when you're calculating the percent change for your assignment 6. Remember, we're not quite done yet. We also, to get it to a percentage, we need to multiply by 100. So after we've done this and included that final close parentheses, we can go on our keyboard Shift and then hit 8. That gives us our multiplication sign, and then we can type in 100, and then there we go. Now we've got our equation. Okay, it's the same equation from our PowerPoint. Now we're ready to calculate the percent change. All you have to do now is just click Enter on your keyboard, and that should calculate the percent change for us. If we go back to question 7, it says in parentheses, round to the first decimal place. So let's do that. Let's decrease the decimals. So if we go to Home, and then if we go to that function again, decrease decimal, we can do that. And we can decrease the decimal to where we have 1 decimal spot, 1 place to the right of the decimal. And in this case, we get a percent change of 10.1%. Okay, so we can include that. That's our answer there. That's our percent change. That's our answer for question 7. So let's report that, 10.1. And then, yeah, make sure when we report percent change, we express it as a percentage. So make sure to include that percentage sign right after the value. Okay, let's move on to question 8. It says 8, the percent change calculated in the previous question, question 7, indicates and we have multiple choice, either a minor, small, moderate, or large increase. So if you take a look back at question 7, we just calculated the percent change. We calculated a positive percent change of 10.1%. Because it's positive, what does that mean? Again, it talks about this in the PowerPoint. A positive percent change indicates an increase from the pretest to the post-test. So anytime we have a positive percent change, that indicates an increase from the pretest to the post-test. And so in question 8, now we're trying to determine how large that increase was. Remember, percent change, and again it talks about this in the PowerPoint, percent change, it is a measure or a statistic to quantify the practical significance. How big, what's the magnitude of the mean difference? And so again, that's what we're trying to determine here for question number 8. What is the magnitude, what is the practical significance of this difference, of this mean difference? In order to determine how large, okay, and to answer this question for number 8, how large this percent change is, if you look back at the PowerPoint, and I'll pull it up again, I'm going to put it over here on this side now. And if you look at this slide right here, this is where it includes the guidelines to interpret the percent change. This is how you're going to answer number 8, okay? You're going to look at this slide here. Depending upon your percent change, okay, that's going to dictate your answer here for question 8. So we calculated in this video here a positive percent change of 10.1%. How large is this percent change? Well, it's positive. So if we look at our slide here, we know that it's going to be one of these here, because this is all for positive percent changes. Okay, so we already know that our answer is going to be one of these listed here under the positive percent change. Because this is positive, okay, we're going to look over here. That's where our attention needs to be drawn. Again, if we had a negative percent change, we would obviously look down here. Okay, we would look down here. A negative percent change indicates a decrease. Indicates a decrease from the pretest and post-test. If this was a negative value, then we would draw our attention here to the negative percent changes. But because we found a positive percent change, yeah, we're going to look right here. Now, 10.1%, positive 10.1%, where does that fall under? Which one of these does that fall within? Which range? It falls within this one. 10.1% is in between 10.0 and 19.9%. And that indicates a small increase. So that's going to be our answer. And so our answer for question number 8, again in this example, is going to be a small increase. So I'm going to bold and highlight there to indicate my answer. So yeah, because our percent change 10.1, positive 10.1% falls within this range here, okay, we know that this percent change now is indicative of a small increase. And so again, this is indicative of the practical significance. Remember, the statistical significance, that's what we solved for up here. The p-value, that determines the statistical significance. Again, like we talked about earlier, if it's less than the alpha level, then that indicates a statistically significant mean difference. However, to determine the practical significance of the difference, that's where this percent change comes into play. When we compare pre-test versus post-test scores, yeah, oftentimes we calculate this statistic here, this percent change. And again, it just gives us an idea of how big, how large this difference is. Again, if we were to just strictly look at the p-value, that really doesn't give us any information on how big the difference is. Okay, all we know from the p-value is if it's statistically significant or not. By looking at the percent change, we're getting more information. Okay, now we're discovering, okay, we found a statistically significant difference earlier. How large is that difference? Is it minor? Is it small? Is it moderate? Is it large? And in this particular case, in this example, we found a small increase. Okay, a percent change of 10.1% is indicative of a small increase. Okay, let's move on to question number 9. 9 says we're going to create a line graph showing the mean 6-minute walk distance and standard deviation for the pre-test and the post-test. So to do that, we're going to do that over here in Excel. We're going to create our line graph in Excel. To create a line graph, what we're going to do is we're going to go over to Excel, and the first thing we're going to do is we're going to highlight, so click and hold and highlight the pre-test and post-test labels here, and also highlight the means for the pre-test and post-test, just as I've done and just as I'm showing you here now. You're going to do the same thing. Highlight the pre-test and post-test and the means. After you've done this, then go to Insert, go to Charts, go to this one here, insert a line or area chart. Again, we're inserting a line graph or line chart. Click on it. And then the specific one we're going to include or insert is this one here, this line with markers. That's the one that we're going to choose here for our line graph. So click on this one, line with markers. And then there we go. There's our line graph. Now, obviously, we're not quite done yet. In order to make a high-quality graph, we need to follow these steps here. So let's do that. It says include labels for both the horizontal and vertical axes, size 11 font. Label the horizontal axis time and the vertical axis 6-minute walk distance in meters. So let's go ahead and do that. To add those axes labels, highlight the graph just as I've done, go to Chart Design, go to Add Chart Element, go to Axis Titles. Let's do the horizontal first. It says for the horizontal axis, let's label that time. So I'm going to label that time. I'm also going to, if we go up to the Home tab while this is highlighted, I'm going to change this to black font. Okay, black font up here just to make it a little bit easier to see. I'm going to bold it just like it is here in the problem. And then also too, it says make these axes labels size 11 font. So you can see here while it's highlighted that it's size 10 font. Let's increase that to size 11. Make it a little bit bigger, a little bit easier to see. Let's do the same thing for the vertical axis. Highlight the graph, go to Chart Design, go to Add Chart Element, go to Axis Title, go to Vertical, and then let's change that vertical title to what it says here, 6-minute walk distance. And then we'll include our units here in parentheses like it says in meters. Similar to what we did with time, let's go up to Home. Let's change the text to black font. Let's bold it. And then let's also to increase the size of this. Again, while it's highlighted, we can do all these things. Increase the size to 11 font. Makes it a little bit bigger, again, a little bit easier to see. Okay, next it says remove the title and delete all grid lines. So here's that chart title here. Let's remove that. You can just hit delete on your keyboard once it's highlighted. Delete, highlight those grid lines, and then hit delete again on your keyboard to delete those. And then in parentheses it says except for the axes, add a gray vertical or horizontal axis if needed. Well, notice here in mine I have a horizontal axis, I have a horizontal axis line, but I have no vertical axis line. So yeah, so if yours is like mine, I need to add a vertical axis line to my graph. So let's do that. To do that, it's fairly simple. Highlight the values on the vertical axis, right click, go to Format Axis, go to Paint Bucket, go to Line, go to Solid Line, and then go to Color, and let's change this to gray. Again, we want to try to make it the same color as our horizontal axis. Our horizontal axis is gray, so let's make our vertical axis gray too to be consistent. You can choose this one. I believe this color here does a pretty good job of mimicking the horizontal axis. And yeah, after we've done that, you can see now our vertical axis has been created, and it looks very, very similar, identical in color to the horizontal axis. Okay, both of them are gray. Very good. Okay, next it says insert major tick marks on the outside of both axes. So let's go ahead and do that. Let's click on the horizontal axis first, highlight it, right click, go to Format Axis, go to Axis Options, go to Tick Marks, go to Major Type, and then go to Outside. That adds a tick mark in between the pre-test and post-test text. Let's do the same thing for the vertical. Highlight the vertical values, right click, Format Axis, Axis Options, Tick Marks, Major Type, Outside, and then that adds tick marks for at each value on the vertical axis. That looks good. The next sentence says, make the line black and include markers for the pre-test and post-test means. So what line are they referring to? They're referring to this line here in the graph. Okay, again, this is a line graph, so hence the line. In the problem here, they're referring to this line. So it says here in the instructions, make the line black. Obviously, you can see the default here is blue, so we need to change the color to black. To do that, if you click on the line to where it's highlighted and then right-click, Format Data Series, go to Paint Bucket, go to Line, go to Solid Line, and then go to Black. And then that changes the line to black, as you can see there. Okay, very good. It also says include markers. Well, we already have markers, right? They're already there. However, in parentheses, it says specifically they need to be black circles, size 8 with no border or outline. So we need to adjust those. Obviously, you can see here that the markers are currently blue. We need to change those to black circles. So again, highlight the line as I've done, right click, Format Data Series, go to Paint Bucket, go to Marker now, go to Marker Options, then go to Built-in, then go to Type, select this one here. This is the circle. This is the circle symbol in Excel. So click on this one, make sure it's selected. And then, yeah, if you go back and look up here, it says they need to be size 8. So let's go ahead and increase the size. Currently they're size 5. Let's increase the size of these markers to size 8. Make them a little bit bigger, easier to see. We still need to make these black circles, okay, these markers. And so if we go to Fill, we go to Solid Fill, and then we go down to Color, and we can change it to black. That makes the circles black. One final thing, it says these markers need to have no border or outline. So if we go to, again, still while these markers are highlighted, if we go to Border, which is down below, Border, and we go to No Line, that removes the outline, that removes the border of those markers, which is what we want to do. That's what the instructions state for us to do. All right, that looks good. So these markers right here that we adjusted, these are the markers for the means. For example, this marker right here is the mean for the pretest. This marker right here is the mean for the post-test. And so in a line graph, what do these markers indicate? Yeah, they indicate the means. And in this particular case, the means for the pretest and the post-test. The next sentence, we need to add the standard deviations now to the graph. The standard deviations are represented by the error bars. And so it says in the next sentence, insert SD standard deviation error bars, both plus and minus direction with cap. So to do that, let's go back to Excel, highlight our graph as I've done, go to Chart Design, go to Add Chart Element, and then go to Error Bars. The error bar that we're going to select is this one here, More Error Bar Options. Now I know, similar to our last assignment, you might be thinking, well wait, Dr. Palmer, there's a standard deviation right there. Why don't we just select that one? That's what we're trying to do, right? Again, it is, okay, we are trying to add standard deviation error bars. However, these standard deviations, if we do it this way, they're going to provide incorrect standard deviation error bars. Obviously, we want our error bars to be correct. We want our error bars to reflect the standard deviations up here, these standard deviations that we calculated earlier. And the best way to do that is to do this option here. So just trust me, okay, when you go to error bars, go to More Error Bar Options. Okay, that adds these error bars. As you can see here, they're highlighted. But we need to make sure that they are the correct error bars. They are the error bars reflecting the standard deviations that we calculated earlier up here. To do that, let's, while they're highlighted, again, you can highlight the error bars like I've done, and then right-click, go to Format Arrow Bars, and then it should come to this option area here. If you look under the vertical arrow bar and if you look under direction, the default right here selected is both. If you look in the instructions, it says, yes, the arrow bars need to be both plus and minus direction with cap for this line graph. And so, yeah, so it's already selected there for us, the direction. Okay, if it's not, make sure it is on yours. Make sure you have this one selected both. What does that mean? That just means that there's error bars going in the upwards direction, the plus direction. There's also error bars going in the downwards direction or the minus direction. Again, you can see that there, right? There's an error bar going up, there's an error bar going down for at each one of our markers there. And so that's what we want, okay? These standard deviation error bars, we want both plus and minus direction. Again, if we go back to our error bar options, and we look in the instructions, it also says we need to include a cap. So if you go to the next one here, in style, you'll notice that cap is already selected for us. Okay, make sure that this one is selected. The cap just indicates this horizontal line here at the top and bottom of the standard deviation arrow bars. Okay, it's just this cap right here, this horizontal line here at the top and the bottom, okay, for each arrow bars that we've added here for the pretest and post-test markers. Okay, that looks good. We have our caps, we have our error bars going in the plus and minus direction. If we go back to our error bar options here, now we have the last thing we need to do, the error amount. This is the part here where we need to indicate in Excel the correct standard deviations for our error bars. In order to do that, we need to go down here and select Custom, and then go to Specify Value. That brings up this window here. What we need to do next is in the positive arrow value, delete everything in this bar to where it's blank. The only thing that should be in there is your clicker that's blinking, as you see mine. Next, you're going to go up here to our data where the standard deviations are that we calculated earlier. You're going to click, starting with the pretest standard deviation, and hold and drag to the post-test standard deviation to where they're both highlighted like mine are now. And then you can let go. Next, we're going to go down to negative arrow value, and we're going to delete everything in this bar to where it's blank. The only thing that should be in there now is your clicker that's blinking like mine is. We're going to do the exact same thing. We're going to go back up. We're going to click on standard deviation, the pretest standard deviation value, click and hold, and we're going to drag to where it also includes the post-test standard deviation value. Now that we have those two highlighted, it shows up here. We should be ready to go. Now let's click OK, and that should add the appropriate standard deviation error bars. Now these error bars reflect the standard deviations that we reported up here that we calculated earlier in our spreadsheet. And so again, make sure and follow those steps exactly the way that I did them in order to include the correct error bars, the error bars that reflect the standard deviations that we calculated earlier, because that's what the instructions tell us to do. Include the standard deviation error bars. Next, it says for the horizontal axis, make the pretest and posttest text black with size 10 font. So what does that mean? That means these here. So these text here, pretest and posttest, they're labeling, okay, the markers, which marker is which. What we need to do, like it says, is it says make these text black. So to make these text black, you highlight them like I've done, go up to Home, go up to Font, Font Color, and then change it to black. Just makes it a little bit easier to see. Also, it says change it to size 10 font. You'll notice while it's highlighted that the font size is 9. We need to increase that to 10. So make sure that the font size there for those two is 10. Next, it says for the vertical axis, make the minimum bound value 270 and the maximum bound value 350. Again, remember the data that I'm using here in this video is different than your data. My data is 6-minute walk distance in patients with COPD. Your data is 6-minute walk distance in patients with chronic heart failure. So again, because your data is different, your graph is going to be slightly different than mine. Now for your graph, you're going to follow these instructions exactly the way that I have them here in question number 9. Again, remember that's one of the things that I grade you on your assignments, is how well you can follow instructions, okay, particularly instructions like these here when you're creating your graph. Again, that's how I grade you. Okay, so not only am I grading you on getting the correct answers, okay, for these previous questions that we've answered, but also too when creating your graph, how well you can follow instructions. And again, by following these instructions, that's going to help you in creating a high quality graph. So when you're creating your graph, your line graph, make sure you follow these instructions exactly the way that I have them. Okay, and that includes here for the vertical axis. Make sure the minimum bound value is 270 and the maximum bound value is 350 with major units of 10. Now, again, because my data is different than yours, my vertical axis minimum maximum bound values are going to be different, okay, obviously. And so I'm going to adjust mine a little bit differently than what they're stated here, okay, because again, my data is different. So to adjust your vertical axis, to adjust your bounds, you can click and highlight like I've done, and then right click, go to Format Axis, go to Axis Options. Here are the bounds here. I'm going to change my minimum bound to, I'm going to go with 230. Okay, yeah, that looks pretty good right there. And then, yeah, my maximum bound, I'm going to keep it, yeah, at 390. So, yeah, so for my data, I'm going to use these for my minimum maximum bounds, 230 and 390. But for your data, okay, when you're creating your line graph, make sure and follow these instructions exactly. Okay, make sure your minimum bound value is 270 and your maximum bound value is 350. Okay, make sure and follow those instructions. Also too, I'm going to, it says here in parentheses, make the major units 10. I'm going to, for my data, make the major units 20. Okay, yeah, it's already there for me, but yeah, I'm going to make the major units 20 for my data. Okay, and again, my data is different than yours, so yeah, my vertical axis is going to be slightly different. Again, for your data, for your graph, make sure your major units are 10. Okay, make sure your major units are 10 here. Okay, because it states it here specifically in the instructions. It also says 0 decimal places. Notice the vertical axis values here. Notice we have decimal places to the right of the decimal. Let's get rid of those. Let's make it 0 decimal places like it says here in the instructions. To do that, highlight the values as I've done, right click, Format Axis, go to Axis Options, then go down here to Number at the bottom. go to category, go to number, and then for decimal places, yeah, change that from 2 to 0. Okay, and the instructions say 0 decimal places, so yeah, let's change that to 0. And then yeah, look what's happened. Yeah, it gets rid of those decimal places. It looks a lot better that way. And then make sure that these values are black text with size 10 font. So again, with these vertical values highlighted, you can go up to the Home tab, make sure that the text is black, and then what else does it say? Make sure it's size 10 font. Currently it's size 9. Let's increase the size to 10. And again, just all in an effort to make it a little bit easier to see. The next step says include an asterisk size 14 font over the center of the post-test marker above the standard deviation error bar if the mean difference between the pretest and post-test was statistically significant. So if you remember from earlier, yeah, we answered this question in question 6. Is the mean difference between the pretest and post-test statistically significant? In my example, yes, it was, right? It was statistically significant. How do we know that? Again, remember from earlier, if we have a p-value of less than 0.05, less than our alpha level, which we did, 0.001 is less than 0.05 our alpha level, then that means that yes, the mean difference between the pretest and post-test is statistically significant. In order to indicate that in our line graph, we include an asterisk. And so because in my example, I had a significant difference between these two, I need to include that. So what I'm going to do is I'm going to zoom in a little bit, and you can do the same thing when you're in your graph, when you're working with these smaller items like asterisks. You can zoom in, makes it a little bit easier to deal with, work with when you zoom in, working with these smaller objects. To insert an asterisk into the graph, make sure the graph is highlighted. Go to Insert, go to Text, go to Text Box, and then you can add your text box to the graph. Doesn't have to be very big, maybe something like that there. And then if you click on your keyboard, okay, while the clicker is blinking inside the box, if you click on your keyboard, Shift and hold, and then click 8, that should provide you with an asterisk symbol that we can use in our graph. Next, I'm going to drag this asterisk to where it's directly over the top of the post-test marker. Again, it says for us to do that here over the center of the post-test marker above the standard deviation error bar. So here's the standard deviation error bar here. It needs to go above that. So yeah, a little bit above that standard deviation error bar, something right about there, right in the middle. That looks pretty good. It also says we need to adjust the size of the asterisk. It needs to be size 14 font. Notice when the text box is highlighted with the asterisk, if we go up to font size, it's size 11. We need to adjust that. We need to increase the font size to 14. Makes it a little bit bigger to see, a little bit easier to see. And then we can readjust the asterisk to where, again, it's directly over the center of that post-test marker, directly over the standard deviation error bar. That looks really, really good. Okay, and again, before we move on, just remember your data is different than mine. And so again, if you don't have a statistically significant difference, okay, again, based on your answer for question 6, if your mean difference between pretest and posttest is not statistically significant, then do not include an asterisk. Only include an asterisk if we have a statistically significant mean difference. If you don't have a statistically significant mean difference, do not include an asterisk. Okay, the asterisk is there to indicate statistical significance. If you don't have a statistical significant mean difference, then obviously you're not going to include an asterisk. So again, be careful with this. Again, again, your data, you might be the same. Okay, you might have an asterisk in your graph, but also too, again, you might not have an asterisk in your graph. And again, what's going to dictate whether or not you put an asterisk in your graph? Whether or not the mean difference between the pretest and posttest is statistically significant. So again, with your data, if your mean difference is statistically significant, then yes, you're going to include an asterisk just like I have here in my graph. But if your mean difference is not statistically significant, you're not going to put a asterisk here in your graph. So again, be careful, okay, and make sure and include an asterisk only if the mean difference is statistically significant between the pretest and the post-test. Next step says insert gray break lines for the vertical axis. Okay, so let's go ahead and do that first. Again, let's zoom in a little bit in our graph. And you can do the same thing like I'm doing. Again, it makes it a little bit easier to deal with these smaller objects when we zoom in. So let's add those break lines, and we're going to add them right here in between the first and the second value on our vertical axis. Okay, we're going to add them right here to our vertical axis, those break lines. Make sure your graph is highlighted like mine is. Then go to Insert, go to Illustrations, go to Shapes, go to Line, and then you're going to create a line just like I'm doing here that goes from left to right. Okay, like this here, slanted in that direction. Notice that the default is a blue colored line. It says here in the instructions we need to insert gray break lines. So with the line highlighted like it is here, if you right click Format Object, go to Paint Bucket, go to Line, go to Solid Line, then go to Color, and then you can change that to gray. And to match the color gray of the axis, you can select this gray right here, and that should work out fine. Remember, with break lines, they come in pairs, and so we need to make a duplicate of this one we just created. To do that, you can copy and then paste this line. Okay, again, with your graph highlighted, you can do exactly what I did, and then you can paste this line back into your graph, and then now you can include these break lines over here where they need to go. Again, they're going to go in between this first value and the second value. That's typically where we put break lines in graphs, and typically they kind of go right here in the middle. Okay, yeah, that looks pretty good. So somewhere in the middle, in between these two values on that vertical axis. Okay, that looks pretty good right there. It says also in the sentence, cover in white the 27 and 270 so that the origin, the starting value on the vertical axis, is 0. Again, remember, your data is different, so your minimum bound value is different than mine. Your minimum bound value is going to be 270. My minimum bound value is obviously different. It's 230. But the same process, the same process can be applied here, and I'll show you. What we're going to do is we're going to cover up this 2.3 right here to where the starting point, the origin, is 0. Again, in high quality graphs, the origin typically is, always 0. And so in order to do that, that's what we're going to do. We're going to cover up these first two numbers. Again, with your data, you're going to have a 270. You're going to have 270 here. You're going to cover up the 2.7. I'm going to cover up the 2.3. To do that, make sure your graph is highlighted like mine is. Okay, where the border is highlighted, go to Insert, go to Text, go to Text Box. You're going to create a text box again. Doesn't have to be that big, just big enough to cover up the 2 and the 3 here. Once you've created your text box, click it to where the border is highlighted like mine. Right click on the border, go to Format Object, go to Paint Bucket, go to Solid Fill, and then change the color to white. Make sure for the line there's no line. Okay, this is indicative of the border. We don't want any border on our text box, so yeah, make sure it says no line here, no border, no line. And then next we can drag the text box, click and drag and hold to where it's positioned, right over that 2.3, to where the 2.3 now is hidden, okay, covered in white, and now only the 0 is showing. So now, again, that looks good. That looks appropriate to where now the origin point is 0. So that's just a little trick in order to do this procedure here. Again, you're going to do the same thing for your graph. You're going to cover up the 2.7 and the 270 so that the 0, okay, the starting point for your vertical axis is 0. Okay, that looks good. I think that's it. I think we're done. So let's zoom out to where we can see the graph in its entirety. Okay, there we go. So now we can see the graph in its entirety. That looks really, really good. A good high quality graph there. I'm going to, real quick with this vertical axis, I'm just going to move it slightly to the left. You don't have to do this on your graph. I just did that on mine just to provide a little bit extra space in between the values and the label here. just looks maybe a little bit better, a little bit more visually appealing. Okay, again, you don't have to do that, but I just did that here. All right, once finished, copy and paste your line graph as a picture in the space below. You can copy it directly from Excel, or you can use the snipping tool on your computer. So again, you can do one of those two options there. You can click and highlight your graph as I've done, and then right click and copy, and then you can paste it back over here. Or you can use that snipping tool like it says. I'm going to use the snipping tool. I kind of like that. And so you can search snipping tool, find it. Let's see if we can get it to work. Go to this try snip and sketch, click on new, and then you can click and drag to where the graph is captured in its entirety. Okay, make sure don't cut off anything. Make sure we see everything, the labels, the values, okay, the axis, everything. That looks really, really good right there. Okay, now that we have this, let's copy it. Go up to copy here, and then we can minimize this, and then underneath our question 9, we can click underneath and then right click and go to paste, and that should paste our line graph down below for question 9. Again, it says down here you may have to adjust the size of your graph so that it fits on this page. Make sure it's large enough for me to see. So if we click and we highlight our graph as I've done, if you go to picture format, again, you can adjust the size this way. But yeah, that looks pretty good right there. That's certainly big enough, large enough for me to see. Okay, that looks good. All right, awesome, cool. So I think that's it. That was our last question that we had to answer for assignment 6, question number 9, creating that line graph. That's a great looking line graph right there. Again, some closing remarks before we finish. Basically, what do we do here today? Okay, remember our objective here today, and if you take a look back up here at the top at the scenario that was given, our objective here was to determine if this exercise program was effective at improving 6-minute walk distance in patients with COPD. That was our objective here. Okay, that's what we're trying to solve, what we're trying to figure out. And again, that's going to be the same objective for you in your assignment 6. You're going to try to determine the effectiveness of the exercise program on 6-minute walk distance in patients with chronic heart failure. Now, to determine the effectiveness, how do we do that? Yeah, to determine the effectiveness of an exercise program, we perform a dependent samples t-test. That's what we performed in question number 4. In order to determine if a intervention, if a training program is effective or not, that's what we have to do. That's the statistical analysis that we need to perform. Once we perform that dependent samples t-test, we get our final output, and from that final output, we look at our p-value, particularly the p-two-tailed value. That's the appropriate p-value that we need to look at and need to report. Because in this example here, our p-value for that two-tailed was 0.001, which is less than our alpha level of 0.05, we rejected the null hypothesis. And by rejecting the null hypothesis, we are concluding that the mean difference between the pre-test and post-test is statistically significant. And so if we take a look back at our graph, again, we can see that here. Remember, line graphs, and again, it talks a little bit about this in the PowerPoint, a line graph is a good visual description of the means and standard deviations of pre-test and post-test scores. And you can easily see in the graph, yeah, we have a significant increase, right? Yeah, we have a statistically significant increase from the pre-test to the post-test. Again, it's statistically significant as indicated by the asterisk. That asterisk indicates statistical significance. And so another way to word this is that, yes, because we found a statistically significant mean difference between the pre-test and post-test, we can conclude that the exercise program in this example was effective. It was effective at improving 6-minute walk distance in patients with COPD. Okay, it was statistically significant. It was effective. Remember, the other statistic that we calculated was the percent change. Percent change is indicative of practical significance. The p-value indicates statistical significance. The percent change indicates practical significance, which is basically how large, the magnitude of the difference. We calculated the percent change here in this example as a positive 10.1%. Because it's positive, we know that it's an increase. It's indicative of an increase. How large is that increase? Yeah, if we looked at when we looked at our PowerPoint, we were able to see those guidelines, and we saw that a 10.1% increase fell within that range of a small increase. So if we take a look at our graph here, even though we saw a statistically significant increase from the pre-test to post-test, it was significant. I'll bet it was small. Okay, so yeah, we did observe a significant increase in the 6-minute walk distance from the pre to the post test. However, it was a small increase, okay, as indicated by the percent change. Now, what are some implications? Okay, so now that we found this result here, we found a statistically significant increase in 6-minute walk distance from pre-test to post-test. What can we take from this? What are the implications? Yeah, for dependent samples t-test, when we look at those types of study designs that use that statistical analysis, these within subject designs, okay, within group designs, one thing that we can gather, one implication is yes, we can use this on future patients, on future individuals. So what do I mean by that? Let's take our example here. Because we found that this exercise program was effective, okay, because it was significantly different, we found a significant difference between the pre-test and post-test, we can conclude that the exercise program was effective at improving 6-minute walk distance. Now what we can do is for future patients, future COPD patients, we can prescribe that same exercise program to help improve 6-minute walk distance in those folks. So yeah, so that's the importance. That's the importance of doing these types of studies where we do these dependent samples t-tests, is we can determine whether or not a training program or intervention is effective. And if it is effective, then we can continue to use that program on future patients. Okay, future COPD patients that come into a doctor's office, right? You know, a doctor, a physical therapist, they ask you, okay, yeah, what program is effective? Okay, is this exercise program, is it effective? Is it statistically, does it result in a statistically significant increase in performance? And again, you can answer that question by conducting a dependent samples t-test and doing exactly what we did today for assignment 6. And if it is effective, then yeah, you can use that on future patients. Okay, you can use that on future patients. And again, because we saw a significant increase, you can expect similar type findings for those patients as well. A future patient that performs the same exercise program can expect similar increases in their 6-minute walk distance. So that's the implications. That's the importance, okay, of performing these types of studies, is that, yeah, we can answer that very important question. Is this particular training program effective at improving performance? Now remember, with 6-minute walk distance I talked about earlier, that's an indication of functional ability. Okay, someone who walks further has greater functional ability. And so yeah, that's another implication that we can take from this particular study here, is because we found this statistically significant mean difference between the pre-test and post-test, we can say that not only was this exercise program effective at improving 6-minute walk distance, it may also be effective at improving overall functional ability, because 6-minute walk distance is an indicator of functional capacity. So yeah, so again, that's another thing that we can take from this, is that this exercise program may be effective at improving functional performance, functional ability, functional capacity in patients with COPD. Now, what if you find, let's pretend here for a second that, let's say we found no significant difference between the pre-test and post-test. Okay, what does that mean? That means that the exercise program was not effective at improving performance, at improving 6-minute walk distance. What if our results showed that? Does that mean our study was worthless? No, absolutely not. Just because we have a study that doesn't find a statistically significant difference between the pre-test and post-test doesn't mean that the study was worthless. Okay? On the contrary, again, just if a study shows no a significant difference between pretest and post-test, if it shows that the exercise program was not effective, what can we take from that? Again, that's a very, very important result. What we can take from that is, yeah, we can tell the physical therapist or the doctor who's ever trying to see if that exercise program was effective or not, we could tell them that, yeah, again, that program, based upon our results on our analysis, that wasn't an effective program. So it may be best if we try maybe a different program. Okay, and so yeah, so again, implications from finding no significant difference is also really important too. Again, that tells us that we need to maybe look elsewhere. We need to maybe try a different program to see if that program may be more effective, okay, than the program that wasn't effective. And so yeah, so just because maybe you don't find a statistically significant mean difference doesn't mean that your study's worthless. Okay, again, practical from, again, using this example here, it just means that, yeah, maybe that particular program that we tried wasn't effective at improving performance in that population. Let's try a different program, and then again, if we try a different program, we can do a similar type of analysis, a dependent samples t-test, to see if that program is effective at improving 6-minute walk distance, improving performance. So yeah, so there's lots of important implications there that we can get from doing these types of studies that use these dependent samples t-test analyses. Okay, I think that's it. After you've answered all of the questions on your assignment 6, make sure, again, type your name here at the top left corner of the page after you've answered all the questions. Make sure and save your assignment to your computer. And then after you save your assignment 6 with all of your answers to your computer, you can go back to Blackboard, and then you can upload your assignment 6 to the appropriate Dropbox on Blackboard, the assignment Dropbox. Okay, I think that's it. Hopefully this video is helpful in answering questions on your assignment 6. Again, remember that your data is different than my data, and so therefore your answers may be slightly different. Some of your answers may be the same, some of your answers may be different, okay, than my answers that I showed here today in this video. So again, just keep that in mind. I hope you all have a great day, and we'll see you next time. Bye-bye.